Okay, now this is recording, so let's begin. Okay, in this chapter for chemical bonding, we're gonna look at these few things here. We're gonna look at the three different bondings: the ionic, the covalent, okay, and also metallic bonding. Now, for these three, for each of them, we're gonna look at what they are. Okay. Next thing, we're gonna look at what type of elements have those type of bonding. Or what types of elements would have those bonding. We're gonna look at how to describe the bonding and its structure. Okay. Then we're gonna look at, in terms of the ionic and covalent, we're gonna look at how to draw the dot and cross for ionic and covalent. And then lastly, we're gonna go look at we're gonna learn how to draw the structural formula for covalent. Okay, so this is in general what we're gonna cover in this chapter 4. Okay, so let's start. Let's go with ionic bonding first. Okay, before that, before we even go into bonding, we actually will need to tackle on why do atoms even combine in the first place. Okay, so to understand why do they even combine in the first place, we will look at this idea of noble gas. Okay, what's so special about noble gases? And then from there, we're gonna go into the idea of bonding. Okay, so let's start. Noble gases, including helium itself, okay, they are the elements in the rightmost group, which is group 18. Okay, so take note, what's so special about them is that they all have full valence electron shells. Okay, and we say that they have noble gas electronic configuration or noble gas electronic structure. And because of this, they have noble gas electronic structure, they are actually stable. And because they are stable, they will not lose, gain, or share electrons. Okay, electrons. Now, and because they are stable, or we can say that they are chemically unreactive, therefore they are monatomic, means they exist as single atoms because they do not combine with other atoms. So you can see here for helium, neon, and argon. For helium, it only has one shell, so the electronic configuration is 2. We actually call this a duplet. Okay, if only the outer shell is 2, we call this a duplet electronic configuration. For neon and argon, the valence electron shell is 8, so we actually term this as your octet electronic configuration. Okay, so that's how the term goes. Next, so once we know that all the noble gases, they are stable because their valence shell is fully filled, we now will also be realizing that, okay, for atoms that do not have full valence electron shells, what happens is that they will combine with other atoms. Okay, they'll combine with other atoms. Okay, this combining with other atoms generally is what we call bonding. Okay, we'll call this bonding. So most atoms do not have the duplet or octet electronic configuration. They do not have the noble gas electronic configuration. So because they do not have that, okay, how do they achieve? So to achieve the complete valence shell of electrons, or to make sure that the valence electron shell is fully filled, what do? They will combine to form bonds, right? So how to form bonds? They can either lose electrons, gain electrons, or share electrons. Okay, so these are 3 ways. Now for the loss and gain of electrons, this one typically we will look at is ionic bonding. For sharing electrons, we will normally look at it from the covalent bonding point of view. And take note, metallic bonding is actually about the loss of electrons. So metallic bonding is just focusing solely on the loss of electrons. And we're going to cover ionic bonding first, followed by covalent, and lastly metallic. Hey, come, let's go. So what is ionic bonding itself? So ionic bonding is the bond between ions. Okay, so before even going into the bond between ions, we also need to ask ourselves, how are ions formed? So first thing, ions are formed because they either lose or gain electrons. So it's either or. Okay, so ions are formed when atoms lose electrons or gain electrons. So how do they do so? Let's look at it. So consider your sodium atom which has one electron in its outermost electron shell. Okay, outermost shell. Because sodium atom electron configuration 281, 1 electron in the outermost shell. So what can happen is that they can either gain 7 or lose 1 electron to form that octet electronic configuration. So key idea here, which is more likely to happen, which is easier. Which is easier to happen? Is it losing 1 or is it gaining 7? So actually the answer is to lose 1 electron. Okay, this one, nope. So this will actually result in sodium, because it's easier, right? So sodium has a higher tendency to lose 1 electron to form its ions. Okay, we'll go into the drawing later on. So but for this one here, you can see here, because it's 281, it will tend to want to lose 1 electron. Okay, instead of gaining 7. So by losing 1 electron, it will actually become a positive ion. So what exactly are positive ions? So positive ions or cations, these two are the same. Okay, it's formed when atom loses 1 or more electrons. So whenever an atom loses electron, it becomes a positive ion or it becomes a cation. Okay, same thing. It's no longer an atom because atoms are overall electrically neutral, but by losing electrons, okay, they are no longer electrically neutral. So why is it because they're no longer electrically neutral? Because for these ions, they are positively charged. There are more protons than electrons. So therefore, they are no longer electrically neutral. Not electrically neutral anymore. And I want you to take note of this. Metal atoms are the one that tends to lose electrons to form your positive ions. Okay? So in general definition, positive ions, they have a net positive charge because there's more proton than electron. Okay, maybe I should just write P greater than E. P greater than E. Okay, and they usually have a noble gas electronic configuration. Why would they have noble gas electronic configuration? It's because the atoms actually lose electrons to form noble gas for themselves to be stable. Okay, now how would you usually draw it? So what happened here is sodium atom 281, valence shell 1. Okay, valence shell has 1 electron, it will lose 1 electron, and then now it will form the sodium ion. So take note, when they form an ion, you will have a square bracket around it. This plus over here represents a loss of 1 electron. How do you know loss of 1 electron? Because right now, if you look at it, there's 11 proton. These two add up, there's 10 electrons. So you can see here there's 1 proton more than the electron. Okay? Therefore, that's why it becomes an overall plus charge. So you can write this as, this is the equation here. Seldom you'll need to write the equation. Most of the time, for bonding, seldom you write this equation. Most of the time you'll need to draw this diagram over here. Okay. Secondly, you also need to learn how to describe it. So the description. So for description here, you'll need to say that the sodium atom, initial configuration 281, loses an electron. Okay, sodium atom 281 loses an electron. So after it loses an electron, what happens? It forms a positive sodium ion, electronic configuration 28. So this is the 5th point. Okay, and achieve a noble gas electronic configuration. Okay, so this is 6. So noble gas electronic configuration. So typically how you describe the formation of the positive cation, okay, you will say the atom loses electrons, form the positive ion, and then what's the electronic configuration, okay, and then what's at the end state. Now, Um, so just an explanation once again of why positive is because sodium ion have 11 protons, but now only 10 electrons. So imagine I got 10, sorry, now I got 11 plus here, because each proton is plus 1, so I got 11 plus. 10 electrons means 10 minus. So realize that overall is a plus. Okay, so it's a sodium plus here. Do take note, okay, remember the charge is always at the top right hand corner. Okay, now what if it's a magnesium? So magnesium 282 at the start. Okay, because my valence electron is 2, I'll lose 2 electrons. So it will form magnesium 2 plus. Okay, because I lost 2 electrons. So 12 protons, 10 electrons. So overall you can see here 12 plus, 10 minus. Overall we will plus 2. Okay, 2 plus at the top. So take note, charge is written as a 2 before the positive or negative sign. Okay, so nothing too fascinating about this. Okay, once again, the description. So how would you write the description for this one? I will say that the magnesium atom, so start from magnesium atom, electronic configuration 282, okay, loses 2 electrons. Okay, so lose 2 electrons to form a magnesium ion, bracket 2, 8, Mg2 plus, to achieve a noble gas electronic configuration. Okay, so the description of how the bonds are formed actually is as such. Right, so same thing, 12 protons, 10 electrons, that's why you got your Mg2 plus. Okay, let's go on. So we have talked about positive ions already. Now let's go on to negative ions. So when are negative ions formed? So the negative ions, or we call it anions, is formed when the atom, or even a combination of atoms, okay, gain. So negative ions are formed by the gaining of 1 or more electrons. Okay, why is it so? Why is it negatively charged? Because there's more electrons than protons. Because you know electrons are negatively charged, protons are positive. So if I got more negative charge, the overall charge is negative. Do note that negative ions are usually formed by non-metal atoms. They'll gain electrons to form negative ions. So I know that metal atoms, okay, will tend to lose electron, and then they will form cations. Okay, whereas for non-metal atoms, they will usually gain electrons, okay, so that they can form anions. So the question is, why is it that non-metal atoms will gain electrons instead of losing? So let's go on to this. Okay, so we look at chlorine as an example. So chlorine has a electronic configuration of 287. So there's 2 ways to form octet. It's either become 28 by losing 7 electrons, or it can become 288 by gaining 1 electron. So which is easier? Obviously this is not easier, right? So chlorine has a higher tendency to gain 1 electron so that it can get a noble gas electronic configuration. So starting from 287, it will gain 1 electron, and that's why it will become 288. Because it gained 1 electron, it is an ion now, so we have the square bracket over here with a charge of negative. Now take note, if it's negative or positive, we won't have the 1. Okay, the 1 is non-existent. So when you just put minus here, okay, it represents 1 minus. Second thing I want to take note, when it becomes an ion, you realize that this electron, okay, X, is from another atom. Since it's from another atom, you want to clearly show that it's not from the this chlorine atom. That's why you use a different symbol. So you can see initially all is this circle, right? So therefore this one I put X. So X is electron from another atom. Next thing to note, see the name change. So it's a chlorine atom become a chloride ion. For metal, there's no such change in terminology, but for non-metal, there is. So you would change the term to end with an IDE when it becomes an ion. Okay? So, After gaining one electron, the chlorine atom is no longer electrically neutral, therefore becomes ion, right? So now it becomes a chloride ion. Since there's 17 protons, so 17 plus, 18 electrons mean 18 minus. Overall, it will be a charge of -1, so therefore we give a Cl minus. Okay, let's see another example, which is oxygen atom. So oxygen atom originally configuration is 2,6. So what happens is that it will gain 2 electrons, so it becomes oxide 2 minus. Okay, because it's 2 minus, because it's 2 minus, it gains 2 electrons, so I have 2 X over here to show that the electrons are from another atom. The overall charge is 2 minus, okay, because it gained 2 electrons. There is actually 2 electrons more than the proton. So you can see I got 10 electron, 8 proton. So 10 minus, 8 plus, overall 2 minus. Okay, so ions are not difficult to draw. Okay, ions are actually not difficult to draw. It's actually very easy to draw. Okay, once just remember, it's always from the atom. You either lose or gain electron, then it becomes your ion. So if you follow this step, this format, your ions will never go wrong. Okay, now these are common ions that you need to know. I'm sorry, but you need to memorize them. I'll just highlight those that you can't get from the periodic table. So for hydrogen, periodic table doesn't tell you much details. So take note, hydrogen typically when form ions is H plus, silver is Ag plus, ammonium even worse. It's not an element. It's like a cluster of different atoms. So NH4 plus. In terms of 2 plus ions, you have iron 2, copper 2, zinc, lead 2, iron 3. Now, maybe I should use a different color to highlight this one. So let's iron 2, copper 2, and lead. I think this one are easier because you can just follow the Roman numeral in the front. So iron 2 obviously 2 plus, copper 2 obviously 2 plus, lead 2 obviously 2 plus as well. Okay. Oh, sorry, still one more, which is iron 3. So iron 3 as well, you can just follow the 3 over here, 3 plus. So those in green are the ones you need to memorize. Those in yellow just need to take note. Okay, just follow the Roman numeral in the front there. Okay, the rest of it just follow the group number. Okay, some follow the group number. So just follow group number for the charge. Okay. Now, do note that ammonium ion is polyatomic. Polyatomic means that more than one atom is involved in its combination, and we call this ammonium ion a polyatomic ion because it is more than one atom that form this particular ions itself. And take note, it is from non-metallic elements, and when non-metallic elements come together, actually covalent bonding is involved. Okay, later on we'll go through a little bit more of this. Okay, next one. Let's go to here first before we go into the negative ions. So this one here, they say it's unusual to find ions with a net charge of higher than +3. So why is it so? Actually, I'll tell you, it's common sense. Very common sense. Okay, it's really because once it reaches 4, it can either lose 4 or gain 4, right? Once it goes more than that, it's actually easier to gain than to lose electrons. Okay, that's why 3 plus is the max normally you will see with regard to ions. Okay, 3 plus. You will not get 4 plus, 5 plus, 6 plus, seldom. Okay, next one, negative ions. I'll just highlight those that I think you can't easily find from periodic table. So hydroxide, you will need to memorize nitrate, manganate 7, carbonate, sulfate, and phosphate. All of these you need to memorize them because they are very common ions. You just need to take note of them very clearly because a lot of formulas will be involving them. Okay, knowing what elements is involved and what's their charge. Elements involved, what's their charge. No, elements involved, what's their charge. Same thing, okay? Elements involved and their charge. You realize that most of this actually bonds with oxygen. Okay, if you see all these highlighted in green, it's actually oxygen with another element. Okay, that itself will help. Okay, now, do take note. Once again, all of these are polyatomic ions. Polyatomic ions, you can see here, is that generally, you have your non-metals, forming the ions. Generally cluster of nonmetals forming the ions. Okay, and because it's the cluster of nonmetals forming the ions, these nonmetals actually would have covalent bonding in them. Okay, so just take note, a lot of O-level questions or even prelim papers, they tend to like to test you which substance or which substance or compound, okay, have both ionic and covalent bonding in them. So how do you know? It's really when you see all these polyatomic, the polyatomic ions generally has covalent bonding in them. Same for ammonium. Okay, this non-ammonium ion here also have covalent bonding in it. So because it's an ion, definitely there will be ionic bonding. And because it's non-metal inside, this polyatomic this polyatomic ions have covalent bonding within it. So you think of it as covalent bonding within, and then the between ions, that's ionic bonding. So that's why there's both ionic and covalent. Okay, now, so we have gone through in terms of the common ions, how to draw the ions already. Okay, now let's go on to exactly what is this ionic bond. So we learned about the formation of ions. Next is really about what exactly is this ionic bonds. So ions of opposite charges, they can actually join by this thing called your ionic bonding. So it's actually the attraction between your ions. Okay, they are like the north and south poles, but north and south poles, these are magnetic forces. In this case here, they are not magnetic forces. This is actually called electrostatic attraction. So electrostatic attraction and magnetic attraction, they are different things. Okay, so this one is because electrostatic is because of the plus and minus. Okay, so that's what we call electrostatic. Usually we won't say electrostatic attraction alone, we will say electrostatic force of attraction. Okay, so this electrostatic force of attraction is between the ions of opposite charges. Now take note, it must be plus and minus. Plus actually will repel, minus will actually repel. So they must be plus and minus in order for us to really look at this thing in terms of the ionic bonding, where there's an attraction. Okay, so ionic bond is the mutual electrostatic force of attraction between ions of opposite charge. If you ask me, I'll add in another word here, strong. I'll cancel the word mutual. Okay, so ionic bond is a strong electrostatic force of attraction between ions of opposite charge. And I want you to just highlight this whole thing here. Okay, because this is a common phrase that you need to note. Okay, you need to draw quite a fair bit. Or you need to write quite a fair bit. Not draw, sorry. So how do you form the ionic bonds? Is when you form a positive ion, so formation of cation. Then at the bottom, you got the formation of anion. And when you have a cation and anion, because this is positive, this is negative, you have a mutual attraction. Let's cancel this word out. We will say that there's strong electrostatic force of attraction between the oppositely charged ion. Between the oppositely charged ion. Okay? So this is how your ionic bonding works. Now, usually it's not just one sodium atom forming a sodium ion, one chlorine atom forming a chloride ion. Normally there will be a bunch of sodium atom, a bunch of chloride ions. Okay, that's actually what happens. So do take note, the force, the electrostatic force is actually very strong because it is actually at very close range. Okay, so that's why you realize I keep emphasizing on the word strong. Instead of just saying that it's electrostatic force, I just add the word strong at the front. Because at this part here, you can see they explain why is it strong. It's because they are very close together, and hence this bond is very strong. Okay, now, so this is the description of the bond itself. We have described how ions are formed. We have described how the attraction is. Next, we need to learn how to draw to represent it. So to draw to represent your ions, we actually use the dot and cross diagram. Okay? So usually dot represents the electrons for the atom of one element, cross represents the electrons of the other element. So usually it's dot and cross. Okay, now I want you to look at this diagram here. This diagram actually only show the valence electrons, or show the electrons in the valence shell. If the question, so this is I need to take note. If question never state draw valence electrons only. Or if they never say this, you will actually need to draw all the electrons. So in actual fact, in this question, if let's say nothing stated here is to draw valence electrons only, what I'll need to do here is actually to draw this. Okay, so sodium actually is 28. The sodium ion is 28. For chlorine, it's actually 288. So I need to draw 2 more shells inside. Cross, 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 cross. Okay. Once again, take note for anions, because, for example, chlorine, in its formation, 1 electron is actually from another atom. So you realize if chlorine electrons are cross, there'll be one of them that is a dot because it gained 1 electron from somewhere else. In this case, it is from the sodium atom. Okay. So do take note, there's actually no difference between the electrons. This is actually just the dot and cross is for us to show in terms of where the electrons is gained from, where the electrons are lost. Okay. Next. Drawing wise, I think you just need to be able to form ions, and then you just link them together. Okay, so after you know how to draw the ions already, then you just need to add them together. Add them together. Okay, that's your typical dot and cross diagram. Okay, so I want to emphasize again, take note, because they're ions, you always have the square bracket. And next thing, the charges are always on the outside. Okay, next. Now, ionic compounds are usually neutral substances. They consist of ions of opposite charge held together by ionic bond. Now, take note, they are neutral. So, although ions are positive or negative charge, but once they form the compound, they're actually neutral. Okay? Ionic bonds, let's not use the word ionic bonds. Let's just cancel this. Let's just put strong electrostatic force of attraction. Okay, between the positive and negative ions. So we can see on page 65, most positive ions are formed by metal atoms and negative ions are formed by non-metal atoms. Okay? So in this case here, ionic bonds are usually formed between metals and non-metals. So I want you to put exclamation mark here. Just take note of this following phrasing, that ionic bonds are usually formed between metals and non-metals. Now, back to this whole neutral substance. Why ionic compounds are neutral substance is because actually ionic compounds, they have no net charge. Overall, the charge is 0. Why? Is because for your compound to form, the total positive charge from the positive ions must be equal to the total negative charge from the negative ions. Okay, and because of this concept, this principle, we will actually be able to know what's the ratio of the ions. Okay, we can actually form the formula. Because of the ratio of ions. So for example, if sodium Na plus, chlorine is Cl minus, you can see plus 1, minus 1. So if I got plus 1 and minus 1, actually 1 sodium will balance out with 1 chlorine. The total positive, total negative, 1 chlorine and 1 chloride ion and 1 sodium ion. You have both of them together, 1-to-1 ratio will be sufficient. And hence the formula for sodium chloride is actually NaCl. Okay? So it's a 1-to-1 ratio. So if you look at magnesium and iodide, so I got Mg2 plus, I got I minus. Mg2 plus and I minus. So what's the formula here? Because the overall charge for magnesium is plus 2, I is just minus 1. The charges are not balanced. I'll need 2 times of this for the charge to balance. So therefore, for every 1 Mg2 plus, I'll need 2 I minus to balance it out. Therefore, my formula will be actually Mg I2. magnesium iodide is made of one magnesium and two iodide together. Okay? How to draw the dot and cross? Typically, this one I should actually say show valence electrons only. Right? Valence electron only. Therefore, magnesium in the middle, Mg2 plus. Iodide, because it's minus, means must have gained one electron from somewhere else, which is the magnesium. Therefore, it's like this. Okay, I minus. Now, one thing to take note, you can actually also draw it as such. So, instead of drawing two iodide ion, you can actually do this. Mg, circle, 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 circle. Okay, so Mg2 plus. You can also draw, then after iodide ion, I'm going to draw here. Cross, 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 dot, minus. Then because I know that I need 2 chloride, so I just put a big 2 in front here. So take note of the position of the number, okay? I put a 2, big 2 in front of the whole anion. Please don't write 2 over here, this is wrong. The 2 should be in front when you are drawing it out. Okay? Now, in terms of structure, so I went through the bond, formation of ions, went through talking about what ionic bond is, went through about how to draw dot and cross diagram. Then now we can look at how do you describe structure. So for ionic structures, the positive and negative ions actually exert the electrostatic force of attraction all around themselves. Okay? This means that the positive and negative will attract each other. Okay? But also if they are a certain distance away, so if let's say I got another negative ion, they are a certain distance away, they will still attract. Okay, just that because they are slightly further, it will be weaker. So for ionic structures, actually it wouldn't be just one positive ion, one negative ion. In general, it's actually a very giant structure. It's like uncountable number of ions. So in solid state, the ionic compounds actually exist as a three-dimensional giant lattice structure. How do we describe this ionic structure? We will actually say that it's a giant ionic crystal lattice structure. Okay, so this whole gigantic term. So whenever I ask you what's the ionic structure, you need to say this giant ionic crystal lattice structure. Okay, so it's mentioned here. Okay, and this whole structure actually is consisting of alternating positive and negative ions, like what you see here. So negative, positive, negative. So positive, negative, positive, negative, positive, negative. And you realize that surrounding the negative is all positive. Surrounding the positive is also all negative. So they will alternate between the positive and negative. I just want to highlight this. Okay, for sodium chloride example, if you were to see here, let's say this is the positive side, right? Positive. It's actually surrounded by 6 negatives around it. And then you say, it's a 1-to-1 ratio, right? But if you look at diagrammatically, let's just focus on one positive. You realize on the left side, there's 1 negative. Right side, 1 negative. On top, 1 negative. Bottom, 1 negative. In front of it, 1 negative. Behind it, 1 negative. So every positive is surrounded by 6 negative. The same is also true. For every negative is surrounded by 6 negative. Every one negative is surrounded by 6 positives. So each sodium ion is surrounded by 6 neighboring chloride ions. Each chloride ion is surrounded by 6 sodium ion. Okay? So just take note in terms of the way how it is being described over here. Okay, in terms of what is surrounding it. But just take note, ratio is still 1:1 if you just count the total number of positive and total number of negative. Okay? Okay, done with ionic. Now let's go on to covalent. So covalent bonding actually happens when atoms share electrons. Okay, covalent bonding happens when atoms share electrons and actually exists between non-metals. Okay, let's go dive into it. So before we look at covalent bonds, I want to highlight one new idea here. Before we go to covalent bond, right, I just want to highlight what covalent stands for. So the word covalent is actually split into 2 words. So co represents sharing. Valent represents the valency, or we talk about the forming of bonds using the outermost electrons. Okay? So it's about sharing the outermost, sharing the electrons in their outermost shell. So that's actually what covalent bonding is about. So sharing electrons in the outermost shell. And hence, in order for us to really dive into covalent, we first need to understand this idea of what exactly is this valency. So valency refers to the number of electrons that must be lost, gain, or share in order for the atoms to gain a noble gas electronic configuration. This applies not only to covalent, this also applies to ionic, this also applies to metallic. Because you see, can you see loss, gain, or share? So it can be applicable to actually all three. So what's the valency? How do I know what's the valency of the elements? Okay, how do I know the valency of the atom of the elements? So it actually follows the group. So I have a group 1, group 2, group 13, group 14, group 15, group 16, group 17, and then group 18. Okay, group 18. Now, group 1, the valency will be 1. Group 2, valency will be 2. Group 3, valency will be 3. We know this because we know that group 1 elements tend to lose 1 electron because electronic configuration 281 or 21 or 2881. So lose 1 electron, right? So realize the valency of a group 1, group 2, group 3 will just follow the group number lah. Group 4 onwards. Group 4 actually valency is 4. Now, group 4 doesn't form ions. So what is this 4 about? So 4 represents actually the number of valence electrons that were involved in bonding itself. Group 15, 16, 17, 18, the valency will actually go 1, 2, 3, 4. It will then subsequently become 3, 2, 1, 0. So this valency over here, you can always write it on your periodic table at the start of every single exam or test. It will actually help you determine the number of bonds formed, what's the charge that we form. Okay, it will actually all follow this valency. So it's a very useful number if you know how to apply them properly. Okay, now let's go on to now talk about the covalent bonding itself. So for chlorine, let's use chlorine example. So chlorine each have an electronic configuration 287. It means that they are all both short of 1 electrons. The other way to look at it is chlorine is actually from group 17. The valency is 1. Okay, the valency is 1. Okay, so in order to attain the noble gas electronic configuration, okay, we will say that they will need to share 1 electron. Or we can also think in terms of forming 1 bond. Okay, the forming 1 bond concept later on I will go through a bit more. Okay, so but they will need to share 1 electron, right? So let's carry on from here. So what I know is that chlorine has 7 electrons. They will share 1. The left side chlorine will share 1. The right side chlorine will share 1. So what's going to happen here is we'll have now the 2 chlorine when they come and bond, there will be this overlap region. Okay, and this pair of electrons, satu, dua, these 2, okay, that is being shared, right? Okay, these 2 electrons are in the overlap region. It means that they are both shared between the 2 electrons, the 2 different atoms. Okay, so imagine this green circle represents the chlorine on the left hand side. Okay, then how many electrons does the chlorine on the left hand side have? 1, 2, 3, 4, 5, 6, 7, 8. 8 in the valence shell. It now has a noble gas electronic structure. Let's look at the right hand side. Anything within this yellow circle means that it belongs to the right hand chlorine as well. So if I were to look at it, it has 1, 2, 3, 4, 5, 6, 7, 8. So 8 valence electron. So therefore, you know, by sharing that each one sharing 1, it actually gives this noble gas electronic configuration for both the atoms. So these electrons in the middle here, they are called the bonding pair. So they are called the bonding pair of electrons. And one pair of electrons form a single covalent bond, which I mentioned here, 1 bond. Right, forming 1 bond. So one bonding pair gives you 1 covalent bond. So if I want 2 covalent bond, how many bonding pair would that be? This will be 2 bonding pair. If there are 2 bonding pair of electrons, actually it means that 4 electrons are involved in the overlap region. Okay? Now, once the 2 atoms form a covalent bond, we now call this a molecule. Okay? We now call this a molecule. Now, This diagram here can also be represented by what we call a structural formula. So the structural formula ignores all the electrons that are not involved in bonding. It just focuses on the electrons that's in the bonding part. So therefore, I got one chlorine on the left, one chlorine on the right. The bonding pair forms a single covalent bond. Therefore, this is the single covalent bond. Okay, so the single line there represents the single covalent bond. To draw the dot and cross diagram for the covalent bond, just take note, you will need to know the molecular formula, structural formula, and the dot and cross diagram. Okay, this is how I'll normally do. From the molecular formula, I'll draw the structural formula. From the structural formula, I'll go on to draw the dot and cross. So this is the approach in drawing it. I will share more a little bit later. Okay, I'll share a little bit more later. Now let's go on to understand this covalent bond first. In covalent bond, since the electrons are shared so closely that the shells overlap, actually the bond is very hard to break. So actually your covalent bond within the molecule, okay, is strong. And it's not just about overlapping. If you think about it, the electrons here, something is holding it, right? So what is holding it? Think of it like a handshake. So the chlorine here actually has protons inside, right? Many protons inside, right? Okay, the nucleus here also has protons inside. So the protons are like tugging onto the electrons. So it's very close to electrons and holding it very tightly there. So actually your covalent bond is actually the attraction between this nucleus in the middle and the shared electrons, nucleus of each atom in the middle of the atom, and the shared electrons between the two atoms. So this covalent bond actually is strong. Okay, it's actually a very strong bond. Now, so there's a single covalent bond. Then question is, is there valency 2? Then I found 2 bonds. Answer is yes lah. So for oxygen atom, it has 6 electrons in its outermost shell. If you were to look at the periodic table, the oxygen is in group 16. The valency is 2. So actually, it will form 2 bonds. It will actually share 2 electrons. Okay, you can see it from both sides. Okay, so to form your octet electronic configuration of 2,8, the 2 oxygen atoms must combine to give you the 2,8 lah. So how do you go about doing it? So for the oxygen, each oxygen will actually share 2 electrons with the other oxygen atom. So we can see here, oxygen, each one share 2, and hence you got this overlapping circle with 4 electrons in between. Okay, and hence we know that it's an O double bond O, and represented by this double line here. Now you are saying, you say molecular formula, structural formula, dot and cross. How do you actually do it? Because I don't see it happening here. So now let me show you how I go about doing it. So I will start off with molecular formula. So the molecular formula we know is O2. So O2, what does it mean? So I'm going to go to the structural formula now. I know that I must have 2 oxygen side by side. Okay? Now, you realize the structural formula tells you the arrangement. But the question is, the structural formula has the bond, right? How many bonds does it have? So you know that the valency is 2. Means that each O must form 2 bonds. And you know that in order to form bonds, it must be with another atom, right? So the left oxygen must form 2 bonds. Who can it form bonds with? The right oxygen. So I'm going to draw 2 lines from the left to the right. Can see here, left side form 2 bonds with the right side. So now I know that the left oxygen settled in terms of the number of bonds it needs. Let's look at the right side. Right side also need to form 2 bonds with the oxygen on the left. I look at it, down here also already got 2 bonds already. So therefore actually the right side settles as well. So I know O2, the structural formula looks like this, as what is seen over here. From the structural formula, I'm going to do the dot and cross now. How to do the dot and cross? So I know that as long as there's a bond between, so there must be overlapping region. So O Draw one shell. O will draw another shell with an overlapping region. There's 2 bonds here. Each bond represents 1 bonding pair, which means 1 cross, 1 dot. So if I got 2 bonds, so it should be cross dot, 1 bonding pair, cross dot, another bonding pair. So I'm done with doing the bonding electrons here. So now this dot and cross are. Okay, then the question is, am I done? How come they got like all these electrons over here? Okay, all these electrons over here. So for these electrons over here, how to go about managing them is to compare the valence electrons, okay, and the valency. So oxygen is in group 16. So I know that the valence electron is 6. Okay, equals to 6. The valency of it is 2. So out of the 6 valence electrons, 2 electrons are involved in bonding. Valency 2 means 2 electrons are involved in bonding. So 6 valence electron, 2 involved in bonding. How many is not involved in bonding? It will be 6 minus 2. So I got 4 electrons not involved in bonding. So 4 electrons not involved in bonding. Okay. So therefore, what I'm going to have here, I'm going to draw 4 electrons on the left side, not involved in bonding. And because it's dot and cross, right? If it is cross on the left side, the right side, I'm going to draw dots. So another 4 electrons not involved in bonding itself. Okay. So this is the dot and cross diagram for oxygen. So you can see here how I from molecular formula translate to structural formula. And then from the structural formula converts to the dot and cross diagram. So this is how I go about doing this part over here. Okay. Now there are other ones to look at. So you can try to do for nitrogen as well. Okay, try to do for nitrogen as well. Okay, see how you can get to do the step from molecular formula to structural formula to dot and cross. Okay, you can go and try this. Okay, for your own practice. The answers are here. Okay, so you can go and try it out. Okay, next one. For those are relatively easy because it is just 2 atoms. Okay, and they have the same valency, same valence electrons because it's the same element. What if I got different elements, right? So that's where we can test it out now. So for molecules with different elements, okay, there's one key principle I need to take note. So all atoms will usually bond to the single central atom. Okay? Single central atom. So for example, what do I mean by this? If I got H2O, what is the single central atom? It will be oxygen. So H2O, that's a molecular formula, right? Molecular formula. I'll translate this into the structural formula. So structural formula tells me how they bond and the arrangement as well. So I know O is in the middle because that's a single central atom. The H will bond to it. So actually the H will surround it. Okay, the H will surround it. Now, in terms of valency wise, I need to take note. H, the valency is 1. The number of valence electron is also equals to 1. So take note of this over here. So let's go for this. So I will normally not do the central atom first. I will do the surrounding atoms. So H will form 1 bond, and the bond will only bond to the central atom. So H valency 1 means will form 1 bond. So this H will form a single bond with the O in the middle. Another surrounding H will form a single bond towards the O. So I'm settled. Once I'm done with the surrounding, so I'm done with the surrounding atoms. So this is the first step. Second step, then I'll look at the central atom. So for oxygen, okay, for O, it is group 16, which means that I'll have valency 2, means it'll form 2 bond. Valence electron will be 6, because group 16. So take note, valency and valence electron, be clear, be able to separate what they are. Okay, if you have issues, please go and approach your teachers. Okay, so because I know that to draw the structural diagram, structural formula, I'll need to focus on the valency. So oxygen having valency 2 means that it will form 2 bonds. So I look at my oxygen over here. Does it have 2 bonds? 1, 2 surrounding it. So you realize that once you have settled the surrounding atoms, you most probably have settled the central atom. Okay? So once you're done with structural formula, we can do the dot and cross. So how to do the dot and cross? Same thing, O in the middle. Because there's a bond on the left, bond on the right, so I must have overlapping region on the right side, overlapping region on the left side. Right and left. One line, one single covalent bond represents one bonding pair. One line over here represents one bonding pair. Okay, so I've settled in terms of the bonding electrons. Now I'm going to, so the first part is always settle the bonding electrons. Second part is to look at the non-bonded electrons. So how to know how many non-bonded electrons you draw? Just take the number of valence electrons minus the valency. So hydrogen has 1 valence electron, and 1 electron is used for bonding, which means that there's no electron left that's not bonded. So therefore, for hydrogen, I don't need to care about the number of non-bonded electrons because there just simply isn't any. How about for oxygen? Group 16. I got 6 valence electrons, 2 used for bonding, which means that I got 4 electrons not used for bonding. So if there's 4 electrons not used for bonding, let's assume that dot is for H, cross is for oxygen. So I'm just going to draw another 4 more electrons not within the overlap region. So that's my hydrogen, that's my oxygen. Okay, so this is my H2O, water. Okay, so you can try to draw for your, try to practice your these steps. You can try for NH3, you can try for CH4, okay, go and try for different molecules. Okay, you can even try for CO2 as well. Okay, so these are the 3 common ones that likes to be tested. If you are able to draw them using the flow from the molecular formula to the structural formula to dot and cross, you're quite safe already. Okay, now, so in terms of dot and cross, we are done already. Now let's look at the structure of covalent. So now we are looking at the structure. So this is now structure. Okay, structure of your covalent bond. So in terms of structure, covalent molecules are usually simple molecules. So in terms of structure wise, there's a first kind which is called a simple. Okay, simple. Let me rewrite. Simple covalent molecule. Okay, that's a structure. Okay, what a simple covalent molecule means? It means that they have countable number of atoms in a fixed ratio. So example, H2O water, obviously simple because you got 2 hydrogen, 1 oxygen. Now what if it gets quite big? So wax molecule got 18 carbon and 38 hydrogen atoms. This is still considered simple because we can count. As long as you can count, you know the exact number of atoms, these are all considered simple covalent molecules. Okay? Now, there's another kind when we look at covalent bonding. Another type of structure, which we call it giant molecules. So, the second structure, the name that we typically will call it is giant covalent molecules. Okay, giant covalent molecules. So, if simple covalent molecules are countable, okay, in terms of atoms, okay, if atoms are countable, we call it simple covalent molecules. Those that is practically uncountable number of atoms, we call it the giant covalent molecules. Okay, so what are some examples of them? Diamond. We have silicon dioxide. Okay, we also have our graphite. So these are the 3 common ones that you need to take note of, that we will share a little bit more in chapter 5. Okay, chapter 5. So this is generally how their structures look. We will go more in depth. Okay, so all this will be covered more in depth. More in depth in chapter 5. Okay, so we have looked at what exactly covalent bonding is. We look at the structure. We learn how to draw the dot and cross. We also learn this thing called the structural formula for covalent substances. Okay, so that's what we have covered so far. Now, this part over here, okay, you can just go and read it on your own. Nothing too exciting. Okay, it's practically what I've gone through, but they added a bit more details inside there lah. Okay, they highlighted here on how to go about drawing, but I'll just say that if you're able to do what I mentioned here from the molecular formula, go down to the structural formula, to the dot and cross, actually you're more or less quite there whenever you need to draw dot and cross already. Okay, just want to highlight all the headers here. The group number, I think you know what group numbers is, so not so much issue. Common number of covalent bonds you can form, actually this is the valency. Number of electrons is normally shared, this is actually also the valency. Number of electrons are outermost shell, this is actually the valence electron. So take note, valency is the number of electrons used in bonding. Valence electrons is the number of electrons in the outermost shell. Okay? So be clear in terms of the difference between the valence electrons and valency. Okay, take note of that. Now, after this, we are down to the last part already, which is metallic bonding. So what exactly is metallic bonding? Okay, so when electrons are transferred, that means gain plus loss, we term it as ionic bonding. When they are shared, we use the term covalent bonding. Okay, we know that for ionic it's between metal and non-metal. For covalent, normally it's for non-metal atoms. Now then, exactly what is metallic bonding is actually for metal atoms itself. So for this part, right, so to help you segment the top here, so ionic bonding is really between metal plus non-metal when they come together. Okay, when atoms combine. Okay, so if I got one metal and one non-metal combined, then that is ionic. If I have non-metals combining with each other, it is usually covalent. Then for metallic bonding is when I have my metal atoms combined, metal elements combined. Okay? Why do metals not combine using ionic or covalent bonding? Okay, sorry, got repeat here. Why do they not combine using them is because they will usually form simple positive ions, but they cannot form negative, right? If cannot form negative, cannot form ionic. And they will normally not share because they don't want to take, they always want to give away electrons, right? So therefore, they also cannot do covalent. So metal atoms or metal elements tend to form metallic bond. So what exactly is this metallic bond here? Okay, so you realize they just straight away jump into a structure. So let me highlight here. So metal atoms are held strongly by metallic bonding. What exactly is this? We are going to cover later. Okay, in solid state, these atoms form a giant metallic lattice structure. So this is the structure. So realize the way how metallic bonding versus covalent ionic is in terms of explained here. This one actually straight away start from the structure. So this is the structure for your metallic substances. Okay, how does this structure form? The metal atoms will lose their outermost electrons and become positively charged ions. These electrons now no longer belong to any metal atom. They are said to be delocalized. Can I put one star here? This term delocalized is important. Okay, it's a keyword. Okay, what exactly does delocalized mean? It actually means that they can move freely between metal ions like a cloud of negative charges. So sometimes you tend to say cloud, but rather I'll use the term sea. Okay, because the sea of delocalized electrons, sea of mobile electrons, are the term that you commonly mention. So hence the metallic lattice structure is described as a lattice of positive ions surrounded by sea of delocalized electrons. So this whole thing here is trying to describe the structure, right? So what exactly is a structure? So to frame it out nicely into one sentence or one simple sentence, right? The structure, we call it the giant metallic lattice structure. Now please don't stop here. Please carry on to say that what is this exactly, this giant metallic lattice structure? It is a lattice of positive cations surrounded by a sea of delocalized electrons. Okay, so the positive ions are formed because the metal lost electrons, right? So then the metal formed the cation. Where is this sea of delocalized electrons? It is the electrons that's being lost by the metal. It formed this whole sea of electrons, and hence it is as such. Now, then question is, sure, okay, this is the structure, but where exactly is the bond? What is this attraction? Where is the force? So the metallic bond is the electrostatic force of attraction. I want to highlight here, please use the word strong. Strong electrostatic force of attraction between the positively charged ions, okay, and the sea of mobile or delocalized electrons. Positive, negative, that's why electrostatic. Add in the word here, force of attraction. Okay, what kind of attraction here is the force lah. Okay, so electrostatic force of attraction between the positive and negative. That's why it's electrostatic. So take note the way how it's phrased. So metallic, this is the structure mentioned at the top here. What exactly is the bond, the force of attraction, is the strong electrostatic force of attraction between the positively charged ions and the sea of mobile or delocalized electrons. Okay, so this is actually how it looks over here. So you can see the sodium. So for sodium, you realize that it will form a Na plus and it will give out 1 electrons, right? So this is the Na plus. So plus, 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 plus. You can see many ions form this lattice, this structure. Then this blue part is all the electrons. So can you see this sea of electrons? Okay, actually it mixes in between as well. So the metal atoms become positive metal ions, and then surrounding it is this sea of delocalized electrons. Now, take note, the bonds become stronger. Okay, the metallic bond will become stronger when two things. One, increase the charge of the cation. So the greater the positive charge, the stronger the attraction will be. Two, you increase the number of delocalized electrons. The more negative charge there is, the more negative charge there is, the greater that whole attraction between the positive and negative will be. So if you increase the positive charge, you increase the negative charge, the more you increase them, the stronger the metallic bond will get. Okay, so that's actually how the whole thing generally works. Okay, so this is the kind of bonding and the structure. Now, if you take note that if they ask you to draw, there's no dot and cross to draw for this. It is the model. So every time when they ask you to draw, they're asking you to draw the model. So you should draw like this or like this. So just take note, if it's solid, right, you need to make sure that your it's a regular arrangement, regular arrangement of your positive ions. Okay, and then your sea of delocalized electrons just all around it. Okay, so knowing how to draw the model is key here. Do note they mentioned something here. Okay, the free movement of electrons amongst the evenly distributed atoms is the most important difference between metallic and other type of bonding. These delocalized electrons actually gives the metals quite a bit of its own properties. Okay, so delocalized electron is actually quite a key feature of your metals. Okay, what does it help? It actually helps with conducting electricity, it's high melting boiling point and stuff like this. All this will be covered more in chapter 5 as well. Okay, so as such, actually we are done with the bonding part already. So just a quick summary. So we went through ionic, covalent and metallic bonding. Ionic bonding is between metal and non-metal when they combine. When the non-metal combine with one another, then they form covalent. When the metal atoms come together or the metal elements come together, then they form the metallic bonding. Okay? Now, so this ionic bonds is actually formed by ions. To be more precise, is the negative and positive ions. When they are formed, this attraction between the both of them, okay, the attraction between the both of them gives you your ionic bonding. Now, for covalent bonding, it is when they share electrons. This sharing of electrons, you can see the bonding pair here is being tucked by the two central nucleus. So that itself is your covalent bonding, and this is actually a strong force, strong covalent bond. this is actually a strong electrostatic force of attraction. Electrostatic force of attraction, I'm going to put FOA, between ions, between oppositely charged ions. Okay, then we look at metallic bonding. It's formed by your metal atoms, okay, losing electrons to form this sea of delocalized electrons surrounded by positive metal ions. And what exactly is this attraction? It is the strong electrostatic force of attraction between the positive cations, and to be more precise, you can add in the word lattice. Force of attraction between the lattice of positive cations and sea of delocalized electrons. Okay, so what kind of structure do they have? So giant ionic crystal lattice structure for ionic. For covalent, you can have simple covalent molecule, giant covalent molecules, and last one is giant metallic lattice structure. Okay, so drawing wise, take note. So you need to do dot and cross for this one, ionic. For ionic, you also need to do for covalent. Okay, so this marks the end for this particular chapter. Yep, that's all from me. Bye bye.